In this video, we will talk about heat of vaporization and heat of fusion. We will see how these two different types of heats are related to change in phase. Now, when we say change in phase, that refers to change in state of a material from, let's say, gas to liquid and vice versa, or liquid to solid and vice versa. We will finally solve a few problems to illustrate these concepts. Let's first look at phase change. Now, phase of an object refers to the state of matter of that object. That means, in general, an object can be in one of the three states. It could be in a solid state, it could be in a liquid state, or it can be in a vapor or gas state. Phase change involves change in state of matter, say from solid to liquid, or liquid to solid, or liquid to gas state, or from the gas state back to the liquid state. These phase changes requires exchange of heat. When we say exchange of heat, heat must either be supplied into the system or drawn out of the system. When heat goes into the system, it is positive, as we have seen before, and in the case of phase change, this heat will go into breaking the molecular bonds. Thus changing the state of an object or a material, say from solid to liquid or liquid to gas. When we want to change the state of a material, say from gas to liquid or from liquid to solid, then heat needs to be taken out of the system. Only then this will form molecular bonds and therefore achieve the required phase changes. Interestingly, the breaking of molecular bonds or the forming of molecular bonds during phase changes occurs at a constant temperature. Of course, the value of this constant temperature depends on the material in question. For example, when solid ice melts into liquid water, this process occurs at 0 degrees Celsius. Or when water turns into steam or water vapor, that happens at 100 degrees Celsius, and so on and so forth. Now let's look at the definition of heat of fusion first. Now this is a symbol L sub F. Heat of fusion is defined in the following manner. It represents the amount of heat in joules that is required to change 1 kg of a substance from solid to liquid. Or another way to look at it is that heat of fusion represents the amount of heat that need to be pumped out of 1 kg substance in order to change the state of that substance from liquid to solid. The unit for heat of fusion is quite simply joules per kilograms. As an example, if you look at water, the heat of a fusion is 334,000 joules per kg. Now what that means is, in order to change 1 kg of ice to water at 0 degrees Celsius, one need to pump in 334,000 joules of heat. Likewise, if you want to change 1 kg of water to ice at 0 degrees Celsius, we need to extract the same amount of energy out of the system. Another example is gold, whose heat of fusion is 64.5 times 10 to the power 3 joules per kg. with a corresponding change of phase occurring at a temperature of 1063 degrees Celsius. Similarly, heat of vaporization is defined as the amount of heat needed to change 1 kg of substance from liquid to gas. So in the case of water, if you have 1 kg of water and you would like to change 1 kg of water to water vapor, one need to pump in 2.256 million joules of heat to achieve the phase change, and this phase change would occur at a constant temperature of 100 degrees Celsius. And similarly, if you want to change 1 kg of steam to liquid water, then we need to extract this same amount of heat from the system, and that is also a process that occurs at 100 degrees Celsius. We note here that the SI unit to measure heat of vaporization is joules per kilogram. And this is how we calculate the amount of heat that is required to achieve certain phase change. Assume that you have a sample of a material, the mass of which is mkg. Initially, it is in a solid state, and you want to melt this solid into a liquid state. So what is the amount of heat that you need to pump in? It turns out that the amount of heat that you need to pump in equals the mass of the sample times the heat of fusion of the material that makes up that sample. So in the case of water, this heat of fusion, we have seen the value to be 333,000 joules per kg, or if you're dealing with copper, then the heat of fusion is 207,000 joules per kg. Likewise, if you have a sample of mass mkg, and you want this sample to undergo a complete phase change, say from liquid to gas, then the amount of heat that you need to pump into this mkg of liquid equals the mass of that liquid times heat of vaporization of the material that makes up that sample. So as an example, if you're dealing with liquid mercury, then the value of L sub V is 296,000 joules per kg. Or if you're dealing with, let's say, water, as we have seen, the value of L sub V is 2.256 million joules per kg. Let's look at a problem. How much heat must be absorbed by ice of mass 700 grams at initially minus 10 degrees Celsius in order to transform it to the liquid state at 16 degrees Celsius? Now we are given specific heat capacity of water to be 4190. Specific heat capacity of ice is 2220, all in SI units, and heat of fusion of water is 333,000 joules per kg. Let's see what's happening to the sample of ice schematically. Initially, it is at temperature of minus 10 degrees Celsius. First, it has to go through 0 degrees Celsius, at which point it will have to melt into liquid water at 0 degrees Celsius. Then it is warmed up all the way to 16 degrees Celsius of liquid water. So in order to determine the total amount of heat to accomplish this process, let's divide the entire process into three: process 1, process 2, and process 3. So let's look at the first process. The first process is the process where specific heat capacity is involved because you have a temperature change from minus 10 to 0 degrees Celsius. So the heat that is associated with process 1 is quite simply mass times the specific heat capacity of ice times the temperature difference that is going through. Now the mass is 0.7 kg. I'm converting grams to kg. The specific heat capacity of ice is 2220 joules per kg per Kelvin or per Celsius. The temperature difference is that the final temperature minus the initial temperature. The final temperature is 0, the initial temperature is minus 10. So 0 minus 10. And when you compute that, you will get a value of 15,540 joules for process number 1. Now let's do process number 2. Process number 2 is where you have phase change from ice to liquid. So the heat responsible is the heat of fusion. And we can calculate that using the formula we just saw a few minutes ago. Mass times the heat of fusion of water. So that's going to be 0.7 for the mass. Heat of fusion is given to be 333,000, which will give you 233,100 joules for process number 2. Now finally, process number 3. Process number 3, again, you have a change in temperature from 0 degrees to 16. So you have specific heat capacity in action here. So Q3 is mass times the specific heat capacity of water now, times the temperature change, in this case for process number 3. So the mass is 0.7. Specific heat capacity of water is 4190. The temperature difference is final temperature minus the initial temperature, 16 minus 0. And that will give you 46,928 joules for just process number 3. So adding all these three numbers will give you, for the total heat, the amount of 295,568 joules. And that solves the problem. Problem 2. What mass of steam at 100 degrees Celsius must be mixed with 120 grams of ice at its melting point in a thermally insulated container to produce liquid water at 50 degrees Celsius? Heat of fusion of water is given, heat of vaporization of water is given, and specific heat capacity of water is given. So let's divide the process into steam and ice. So what happens to steam is that initially it is at 100 degrees Celsius and it will turn into water at 100 degrees Celsius, and then it will cool down to water at 50 degrees Celsius. And then what happens to ice? It is at initially 0 degrees Celsius. It will melt into water at 0 degrees Celsius, and then it will warm up to water at 50 degrees Celsius. So what is the mass of the steam that is required to establish this? So let's do the calculation for steam first, process 1 and 2. So first, the mass of this steam is m sub s, we don't know. It is going to turn into liquid water from steam, so you have to use this value right there, the heat of fusion, which is 2256,000, and then it will be cooled down to 50 degrees Celsius water, so that is specific heat capacity. The specific heat capacity of water is 4190. The temperature difference is 50 to 100. So 50 minus 100. So note in process 1 the steam is losing heat, so there must be a minus sign in front. In the second process, the minus sign is taken care of by the temperature difference. Now for ice, again process 1, process 2. Process 1 involves melting, so mass of the ice is 0.12 kg times heat of fusion is 333,000, plus, and then it absorbs heat. Specific heat capacity is of 4190. It goes all the way to 50. So initial temperature is 0, final temperature is 50, and that's the total amount of heat that ice absorbs. So the idea is the amount of heat that the ice absorbs must come from the amount of heat that the steam releases. So adding these two terms must give you a result of 0 because there is no net heat loss. It is a thermally insulated environment. So the only unknown that need to be solved is the mass of the steam, and we can solve that, and it will give you 0.0264 kg, or 26.4 grams, which is the mass of steam required, and that solves the problem. Thank you for watching.